Okay, the second half of section 7.5, which is area of a surface of revolution, is now rotation about the y-axis. In the previous video, we did rotation about the x-axis. So now we're rotating about that vertical y-axis and the coordinate axes. In this section, there won't be any rotation about any non-coordinate axes. That's where things get a little bit messy and a little bit difficult with volumes of solids of revolution. But we don't do that in surface area, mostly just to simplify things. A lot of times what you can do in practice, if you do have a non-coordinate axis of rotation, you can shift your function to be slide it across the coordinate axes with a shift in the x or y variable in order to place that rotation about one of the coordinate axes. And that makes things quite a bit easier. In fact, that's what the y minus a number or the x minus a number for a radius in the cylindrical shells or the disk and washer method actually does anyway. It's literally just a shift. But we don't put that complication into surface area. So let's have a look at rotation about our y-axis or our vertical axis. So we consider a positive function x equals g of, that should be y actually, g of y right here, whose derivative g prime is continuous on the interval c to d. The surface area of the surface obtained by rotating the curve x equals g of y between c and d, so y taking values between c and d about the y-axis, is given by the formula here. This should look somewhat familiar, more or less like what we saw for rotation about the x-axis. Now the difference is for our circumference term, we have 2 pi g of y instead of f of x. Okay, for our arc length term, we've already seen this portion. We have 1 plus g prime of y quantity squared dy. This is dl. Remember, that's sort of the thickness of our approximating band or our arbitrary or general approximating band for our integral. That's what helps us set this up. And it's always going to look something like that. Now, remember we had an alternate form for our rotation about the x-axis. We can use an alternate form here as well. X is equal to g of y. So the g of y in our original formula here can be swapped out by x. So our circumference can be 2 pi x, and then our integral can be done in terms of x. So dl here is written in terms of x. It's very easy to switch out the arc length. It's either 1 plus g prime of y quantity squared dy, or it's 1 plus f prime of x quantity squared dx. Right? So, and again, this is f of x, or f prime of x, quantity squared and square root of all that dx. Right? So really the only thing that's changing that we have to be careful of is how we pick our radius to find the circumference in these. So let's have a look at an example. We're asked to find the area of the surface obtained by rotating the curve y equals cube root of x between 1 and 2 for y values about the y-axis. So y equals cube root of x is this curve. Remember that it passes through the origin and looks something like this. We're only going from 1 to 2 on the y-axis. Note that's from here to here on the y-axis. So for our x values, that occurs at x equals 1 and x equals 8. So we've only drawn that much of the curve. This thing is going to rotate about the x-axis to form some solid. And as usual, we don't really care to try to draw that. It's only going to make the picture more difficult. But we do know that it'll have a little approximating band here. dl is its thickness. And that'll rotate about the y-axis here and form this arbitrary, or this general approximating band that we'll use to set up our integral. So dl, we'll leave that as optional. It can be done in terms of y, it can be done in terms of x. Let's see what the function steers us towards. So it looks like right away, possibly to just to graph this thing or simplify things, we've written this as x equals y cubed. Okay. Then we found that one value and the value of 8 that we saw before for the x-axis. That's some of the details for that. Now we can write this in terms of g of y, a function of y, and that's being equal to y cubed, or x is y cubed, or we can write it as y equals cube root of x. We have two different choices for how we set this up. And in fact, I think this problem really goes nicely either way. In this case, we can just see the demonstration of the full first formula, right, with g of y as our circumference. And that's exactly how I have it set up. So once we've chosen to do this as g of y here, in other words, y cubed for our given function, then we know that dl is going to be written in terms of y, and we'll use that. Okay, so g of y is y cubed, so g prime of y is 3y squared. When we square 3y squared, we get 9y to the fourth. And there's a 1 plus that term underneath the radical from the original formula. And our y cubed that's just from the radius. And the circumference term of 2 pi is now pushed out in front. It's a constant with respect to the variable of integration. And we again see a nice u substitution. Y cubed is 1 power less than the polynomial underneath this radical. And we carry out the u substitution steps here. Again, be very careful with your limits of integration. We have changed variables. You either change your limits of integration to match the variable u, or you just make a note to yourself, y equals 1 to 2, and then back out to be in terms of y before you apply your limits of integration. That's exactly what's been done here. And when we complete this, we've got something that looks like the following. Now, it could be nice to have a calculator here to simplify this a little bit, but or we could write 145 square root of 145. But this is sufficient in this case. Things get a little messy. It's nice to see all of the details here. Of course, WebAssign might want you to do something more accurate with these decimals, so do pay attention to that. Okay, I make the comment in this that it appears we could go either way, right? We could use dl with a function of x, and we could rewrite this with a radius of x. I encourage the reader to try that and see how that goes. Okay, so try to do this in terms of x. It might not, it can be, sometimes these things can be a little deceiving. It might be very difficult to analyze this term in the integral thanks to that square root. That 1 plus f prime of x squared term under the radical might be more difficult if we go the other way. And then we really appreciate the fact that we had this as an option and how much easier this was possibly compared to the other way. So at any rate, try that, see how far you get. If you make it all the way through, great. If not, well, it's nice to know that we had a better way. Okay, so let's look at one more example. It's a bit more of an application, but not by much. We have a parabolic satellite dish. It's to be constructed whose shape, its shape needs to be, will be formed by rotating the curve y equals ax squared about the x-axis for some a value greater than 0, some constant a. The dish is to have a 10-meter diameter and a maximum depth of 2 meters. We need to find the value of a, and we need to find the surface area of the dish. Okay, so first, we're given this and these dimensions for this satellite dish. And when they say a maximum depth of 2 meters, they mean that at the bottom of this dish, when we go from here down to the bottom of the dish, we've drawn this satellite dish with the vertex of it at the origin and the coordinate axes. That needs to be 2 meters. We're not doing an optimization problem here so much as we're just saying that its depth is 2 meters at its deepest point. So remember that it's got a circular face to it. Again, I'm not really trying to draw the satellite dish. I've just highlighted what it might look like, but I mostly want that out of my way. So we know that it's got a diameter of 10 meters. So it means it has a radius of 5 meters, right? Remember, we have y equals ax squared. We can't find the surface area of this until we determine what a must be. So if this is the case, we know that with the origin, with this thing centered at the origin here, the vertex of this parabola at the origin, we need this radius to be 5, its max depth here to be 2, so we have the point 5,2 on this parabola. That helps us determine a, much like what we might do for a line, y equals mx plus b. If we know the slope, we can use a point on the line to determine b, the slope intercept. Here we have a point on the line, and we have one variable we need to know, and that's a. So we use that 0.52 plugged into this, and we determine what a is. A is 2 over 25. So that means that our original formula, y equals ax squared, is y equals 2 over 25 x squared. So now we've got the fully determined formula with the constant for a, and we're ready to do some work to find the surface area of it. We're rotating this about the y-axis, so it's a vertical axis of rotation. We'll notice that our radius for our little approximating band here, let me zoom in to make that more precise. Our approximating band is right here in red. It has a radius of x. So it might be reasonable to try to calculate in terms of x. dl is the thickness, and dl will be, well, if we're going to use this in terms of x, it's the square root of 1 plus f prime of x quantity squared dx. So let's see how that goes. We can always set it up in terms of x and then back out of that and try it in terms of y if it doesn't look good or if we get stuck with the integral. So in this case, y prime is calculated down and to the right below this. We got y prime is 4 over 25x. So that'll plug in here for this f prime of x. We square that. So we have 16 over 25 squared. 25 squared is 625. X squared, 1 plus that, and we've got an x outside here. And it looks like really the name of the game in all these examples is a u substitution. We just keep getting lucky. This is 1 power down from this polynomial expression. We condense it into one term with a u substitution like this, and we're able to move forward with the integral. Again, be careful with the limits of integration. It looks like here we finally changed them. We decided to say, okay, when x is 0, u, based on this function, is 1. Okay, we can see how that comes about. And then when x is 1 or x is 5, it looks like we've got u is 1 plus 16 over 25, which is 41 over 25. Now we can be lazy when we're done with the problem. We've done work on the front end. 0 is replaced by 1 up to a u value of 41 over 25, 1 to 41 over 25. And we don't have to back out of our substitution anymore. So this is the other way of handling those limits of integration. But it's, again, just a straightforward u substitution. When we're done with all these details, we arrive at this expression. Again, something that could be simplified possibly further and written as a decimal, but this is an exact answer. It's really my preferred style of answer. There's nothing we can really simplify in this exponential exponent, or so this fractional exponent. So, or maybe the 25 in the base could be simplified. That's a 5 cubed, 125, and then it's just 41 to the 3 halves. But those are smaller details, and this should be fine on a test. Anything I box in these notes is sufficient on a test. Okay, so again, it might be worthwhile to the reader to just try to set this up the other way. Write this down as a function g of y, and then do this as 1 plus g prime of y quantity squared, square root of all that, dx, or 1 plus g prime of y squared, and then quantity square root, we might say. See how that goes, and if we can arrive at the same answer. If you can, that's great practice. If not, well, then you realize that it's nice that we had this method in exchange for that, something that will get us through the integral that we'd run into, and we could still calculate the surface area. So being able to set up both ways for either vertical or horizontal axis of rotation is critical in order to get through these integrals and find the actual exact values. So that's it for 7.5. It's got a little bit more baggage than the other formulas, but I think it's a little bit more of a fixed environment. There are fewer tricks in the problems, and this formula really kind of has to work on all these problems. There might be 1 or 2 more algebraic tricks I haven't done in the video, so have a look at the book examples and keep an eye out as you work on the exercises for little algebraic loopholes you can exploit, like disguised quadratics underneath the radical. That was always useful in arc length. So otherwise, that should be it, and 7.5 should be ready to go.